Hi everybody, my name's Chris Collison and we're going to continue today with lecture 7 of CHMP 442. It's Quantum Mechanics in Chemistry, and we're working from Donald Macquarie's textbook, wonderful book, and we're going to continue today by looking at section 3.3. And section 3.3 continues to talk about eigenvalue problems. And then we're going to jump into section 3.4, which talks about really the physical meaning of this wave function that we've introduced. And it turns out that it's the square of this wave function that's equal to the probability density. And so now we're going to start to get our heads around how when we observe something, it manifests as a specific outcome, where before we observed it, we could only describe it in terms of its overall probability of happening. And so this has some sort of far-reaching implications. We can discuss that at a future time, but that's really the point of quantum mechanics. It's all probability based, and that's what we're describing, the probability of an event happening. So without further ado, let's jump straight into the math and see you on the other side. So we're working from chapter 3.3, Eigenvalue Problems. And the general situation is that we have our eigenvalue problem, and we have a function that is phi in here. This is the eigenfunction. And when we operate on that eigenfunction with the operator, so here's our operator, we end up with a constant multiplied by that same eigenfunction. So this constant is what we call an eigenvalue. It's important to make a note of this, that it is a constant, or sometimes might be referred to as a multiplier. And so, the operator for linear momentum, by the way, in the x direction, we can go look that up, and by the way, that's in page 148 of the textbook. There's a whole bunch of quantum mechanical operators listed there, but the operator for linear momentum is minus I h bar di by dx. And so I'm just going to formally write that each observable in classical physics has a quantum mechanics operator. And really, these operators, what are they? These are really the bridge between the classical and quantum world, sort of mathematical bridges, if you will. The bridge between classical and quantum worlds. So what we're going to do is we're going to explore how we now might operate on some functions. And so let's suppose that we have 3 functions. So we'll imagine 3 functions: x cubed, cosine alpha x, and e to the I kx. And we're going to ask ourselves the question here, which of these functions are eigenfunctions of the following expression, where the operator here is that linear momentum quantum mechanical operator. So let's jump straight in with number 1 in here, x cubed. So let's apply our operator to x cubed minus I h bar di by dx. We're operating now therefore on x cubed, and that ends up being equal to minus I h bar, and the derivative of x cubed is 3x squared, And when we're doing these questions, when we're tackling these questions, we ask ourselves the question, did we return the same function, in this case phi, when we operated on it? And what we can see here is no way have we returned an x cubed in this particular case. So we would conclude here that no, x cubed is not an eigenfunction. Okay, so let's go take a look now at the second case, cosine alpha x, and we might start looking at this and think, oh wow, chapter 2 was all about these oscillatory functions. It looks good. Maybe we're being set up to think that this is a solution. Let's have a look. So question number 2 is cosine alpha x. Is that an eigenfunction? So we're going to operate on it again. We remember that our operator was minus I h bar di by di x, and we're operating now on this cosine alpha x. And so we take the derivative of cosine alpha x, and we end up getting alpha or minus alpha sine alpha x. Oops. And then so we get minus alpha sine alpha x. Okay, so that equals plus I h bar alpha sine alpha x. But the problem here again, what we have to ask ourselves is, do we see a return of this function in the solution? And so no, we don't. We see a sine alpha x term, but we don't see the cosine alpha x term. So our conclusion here again is no, cosine alpha x is not an eigenfunction. And then let's look at number 3 here. Let's now let's remind ourselves what the function was in number 3. It is e to the I k x. So now we'll apply minus I h bar di by di x to e to the I k x. So the derivative of e to the I k x is we bring the constants down, right? So it's I k e to the I k x. So we'll kind of keep this simple first of all, and then we'll tidy it up. So that's multiplied by I k e to the I k x. So this ends up being, when we multiply those i's together, we get minus 1, and then we've got the minus in here. So we end up having plus h bar k e to the I k x. And so now what we have to do is we say, well, let's go looking. Remember, we're looking for this wave function, the wave function that we started with, and here it is. So we can also say this is equal to h bar k times that wave function. And so the answer here will be yes, a resounding yes. E to the I k x is an eigenfunction of px phi equals p phi. And we're going to say the eigenvalue is, and the eigenvalue is, what is it? It's k h bar, or h bar k, right? However you want to write it. But it must be a constant. So this must be a constant in order to be an eigenvalue. And so you can expect there to be a number of questions in your homework and also exam questions, because this is one of the basic frameworks for quantum mechanics, use of these operators and knowing how to solve these eigenvalue problems. So what we're now going to do is we're actually going to talk a little bit about the first system that we're studying in chapter 3, and we remember our rules, right? The first rule is describe our system classically. The second rule is so replace the observables with appropriate quantum mechanical operators. Then we're going to build a Schrodinger equation, which is an eigenvalue problem. Essentially, we're going to solve that Schrodinger equation, then we're going to apply some boundary conditions. So with that in mind, let's actually switch to a system where we've got, so let's imagine an electron moving in the x direction towards infinity. And we're going to say it's a free electron. What does that mean? That means that it's not impacted by any potential. In other words, we're going to say that v as a function of x is equal to 0. Okay, and so recognizing rule 3 and from prior work, right? So the kinetic energy, therefore, is equal to p squared over 2m. And now recognizing we take these operators, we've got our linear momentum operator. We plug this in, so the linear momentum operator, we're going to square that, right? So minus I h bar di by x. We square that because we're going to have to place it into our equation in here, and we end up coming out with minus h bar squared over 2m d squared by dx squared. And the reason I'm going to put the x squareds in there now, or sorry, the d's rather than the di's, is because we're going to say that this function is a function of x only. So here is effectively our Schrodinger equation. Okay, so we've got, here's our operator in here, this is this h hat, and here's our wave function psi, and that's equal to e psi on the right hand side. So with that in mind, what we can do is go back to chapter 2, and we can recognize from section 2.3, by the way, that d squared x by dx squared plus kx of x equals 0. So that's the kind of expression we've got here, right? So we can rewrite that shortly. We saw that earlier in lecture 6. It's the same format, and we've also recognized that there are some solutions, some general solutions that we expect to work. So let me just write those down in here. So the first general expression that we expect to work would be C1 e to the ikx plus C2 e to the minus ikx. And we can also, we've seen how with Euler's formula we can write something similar in terms of cosine functions and sine functions. So psi of x is also equal to a cosine kx plus b sine kx. So these are sort of generalized solutions. So what we're going to do first of all is we're going to say, let's try these solutions, these possible solutions in our operator equation. And we're going to ask the question, is it an eigenfunction? And if it's an eigenfunction, just like in the previous slide here, so is it an eigenfunction? And if so, what is the eigenvalue? Okay, let's take a look at that next. So let's try one of those suggested solutions, and we'll operate on it with this Hamiltonian operator. What do we get when we operate on it? So minus h bar squared over 2m. Going to keep that outside the brackets here because we're going to multiply that by the operator, by this second derivative of the function that we've got, and that will come out to be minus a k squared cosine kx minus b k squared sine kx, and that will be equal to, let's write this out formally as well, e times a cosine kx plus b sine kx. So we can already see that we've got that this function is an eigenfunction, right? So we're going to see the repeating. We've got the a cosine kx and the b sine kx in here. So we can pull that out. And so once we've done that, we can actually, I'm going to jump to that conclusion here. So that the e in here is equal to plus h bar squared k squared over 2m. Okay, so that's what comes out because the k squared repeats throughout. So this is our solution. Or k is equal to 2me to the half over h bar. Okay, so just solving for k there. So when we look at this now, what else can we pull from this? So we've got our value for e, but really we haven't specified what a is. We haven't specified what b is, and at the moment, let's have a look here. But when we look at the k value, well, the mass is fixed. H bar is a constant. It turns out that k, this other constant that we care about, can take any value because we haven't really quantized. We haven't found a way of quantizing the e in any way. So let's make a quick note of those conclusions here. So a can take any value. Remember, this is rule 4, right? We've solved the Schrodinger equation, but here are these results. So b can take any value, and e can take any value because k is unspecified. So we can say in here there's no quantization apparently. So what is needed next? Well, if you think about the rules that I provided, we still have to consider rule 5. Okay, and rule 5 is really apply these boundary conditions if there are any. Well, at the moment there aren't any boundary conditions because this electron can go where it wants, right? It's moving off towards infinity, so it's not bound to any particular place. But what I'm going to suggest is, suppose we confine that electron to a box. Okay, so let's describe that particular situation. So I'm going to describe a circumstance, and I'm going to say that we are in the x direction in here. We've got x is equal to 0 in here, and we've got a position x equals a over here, and at these very specific positions the potential is going to infinity. So if we want to think about that in terms of gravity, there's an infinitely high cliff, and so the electron can't get out of that box. So what else can we say about this as we set this up? So 0 is less than or equal to x, which is less than or equal to a, and this is implied. What we're also going to do is take a little time out here for a second. So while we're considering these boundary conditions, because I'm going to place the electron, by the way, in that box. But before we go further, I also want to introduce, because this particle in a box description comes up later in the chapter, but I'm going to introduce Max Born's interpretation of the wave function. And this is actually important. And the reason it's important is because we might say, what's the chances that that electron is actually outside of this cavity, of this box that I've provided for it? What are the chances? So here's Max Born's interpretation of the wave function. So we've got psi star. This means it's the complex conjugate of psi, okay? So psi star in here, it's the complex conjugate of psi multiplied by psi of x dx. This entire piece in here, this is what we call the probability density. And it is the physical meaning. So this is the physical meaning of the wave function. So with that in mind, why did I bring this up at this point? So I'm going to say, so we're going to sort of jump up here a second. So what's the probability that A, the electron is in the box, and B, the electron is physically located, so is at x equals 0 or x equals A. So have a think about that. Press pause before we get to the next slide and we'll explain. So I'm actually going to leave you with a bit of a cliffhanger there. So we're going to apply these boundary conditions in the next video, and that's going to take us to a very interesting and critical piece of quantum mechanics called particle in the one-dimensional box, and we can pull a whole lot of stuff out of that about the importance of small masses and the importance of small lengths of the box. So join me in the next video. It'll come up as lecture 8. See you there.